Recording in progress.
So we have learned about the RCNN algorithm. Okay. So we first extract this amount of bounding box, which may contain the object inside. Okay. And actually, it is still large in size. We have to extract 1,000 to 2,000 bounding boxes, but it is still large. But compared to all the bounding box, we may have to extract from the image. If we use the sliding window approach, then that would be like 100,000 bounding boxes. So compared to that, this is a lot faster, right? And using this scheme, it still takes few minutes, but it becomes anyways practical because getting the bounding box from one image, anyways, it could be done automatically within few minutes. Okay, so I mean, this is the first approach that computer vision researchers are proposing a method to apply deep networks in the object detection domain. And also we learned about the fast RCNN algorithm. This algorithm is faster than RCNN algorithm by reducing the number of CNN application, just one, right? Previously, we have to apply, the number of the bounding box times we have to apply this CNN. But here in fast RCNN, we just have to apply one time for the CNN architecture and getting the 2D feature map and apply the ROI pooling to make it into the fixed vector, and then map it to class probability and also the window estimation. Okay, so somehow we refine the initial bounding box. Okay, so that's the fast RCNN, and faster RCNN, it removes the bottleneck in the object proposal side, because it was done by using some clustering algorithm, which is not differentiable. So we remove that which is not, that pipeline is not differentiable. So there's some sub-optimality in their module. So we remove that part as well. So we replace that clustering-based object proposal algorithm by changing it to network prediction. Okay, and it becomes better in accuracy, and also it becomes real time. Okay, so not real time, sorry. It anyways becomes faster than before. Okay, so that's the faster RCNN algorithm. And this is the comparison of three algorithms we have learned. So RCNN, fast RCNN, and faster RCNN here. Okay, and we already see how much they taken for one image inference, and also comparing the accuracy using two types of data. We see the accuracy could be better if we use RCNN. From RCNN to fast RCNN, their accuracies become robust. Okay. And then we learned about the YOLO briefly. So seeing their algorithm, before that RCNN algorithm, they are called as the two-stage algorithm, because at the first stage, they detect the bounding box, and the second stage, they classify those bounding boxes into some classes. So this is what object detection pipeline was constituted before this YOLO algorithm. But YOLO, they are insisting that their algorithm is one-stage algorithm, because they simultaneously detect bounding boxes and also the class probability for local regions. And then they apply some post-processing algorithm, which is called as NMS. This is the non-maximal suppression algorithm. So yeah, I mean, the name is quite intuitive. They will suppress, which is non-maximal bounding box. Okay, so they remain only the maximum bounding boxes. So this is the post-processing approach. So many, given many bounding boxes, and given some score, semantic class probability for each regions, we somehow apply NMS and remain the bounding box which have the highest probability. Okay, so that's the YOLO algorithm. So I mean, originally this YOLO is you only live once, right? So that's kind of the word the young people is frequently used. But this algorithm say replace this live to loop, and they are, somehow enforcing their algorithm is one-stage algorithm. Okay. And for achieving this object detection, they use this kind of architecture. Okay, and what they actually does is they first make grid. So from the image, they divide the width by 7 grid and height by the 7 grid. Okay, so totally there are 49 grid. Okay, you can actually change this hyperparameter. So but you have to train the algorithm again if you change the grid size. Okay, and what do here, this part is, what happened, this part is, for each grid, they infer 2 bounding boxes. Okay. So for each grid, they infer 2 bounding boxes. So because there are 49 grid, and for each grid, we will estimate 2 bounding boxes. So there will be 98 boxes estimated, and that's the result for this. Okay. And another thing we will estimate is for each grid, we will estimate the class probability for semantic classes. Okay. So this color in each region is denoting that some specific class semantic object is there. Okay. So this pink is denoting the bicycle maybe, and this orange color may be denoting the car object, and green is denoting the dog maybe. So anyways, in each grid, they are estimating the objects the grid may contain. Okay, so they estimate these 2 informations jointly from each grid. Okay, and then they apply the non-maximal suppression algorithm to filter out unnecessary bounding boxes, and then obtain the final result. Okay. So, and that is actually happening this part. So these 2 joint mapping, the probability map, and the 2 bounding box for each grid, that would be estimated by this network. So you can see the original input image, their dimension is 448 by 448 by 3. Okay, this is the RGB image whose width and height are both 448. Okay, and they are estimating 7 by 7 by 30 dimensional array. Okay, this is because 7 by 7, this denotes the grid size. Okay, so for each grid, they are estimating 30-dimensional vector. Okay. Are you agree with this? I mean, are you following this? So 7 by 7 means for each grid, we will estimate 30-dimensional vector. Okay? And that 30-dimensional vector looks like this. And as I told you, they are estimating two bounding boxes. So this 5-dimensional vector is containing some information for each bounding box. Okay. So this 5 dimension is for one object, one bounding box, and the other 5 dimension is for containing information about the other bounding box. Okay. So this is actually equivalent to inferring two bounding boxes for each grid. Okay. Are you guys following this? And this part is 20 dimension because it had to coincide to the number of classes. If your application have, for example, 50 classes, then this part may have 50 dimension. Okay, right. And also, if you want to estimate 3 bounding boxes for each grid, then you may can add one more 5 dimension in this whole vector. Okay, are you guys following this? So this vector is meaning that for each grid, we will estimate this 30-dimensional vector that may contain the class probability and at the same time, two bounding box information. So this is actually denoting that this information, okay? The below class probability is for this part, right? For this part. And this is denoted as the upper bounding box estimation result, okay? So, I mean, YOLO is estimating this type of 7 by 7 by 30-dimensional array from the original image, okay? And that is actually represented here as, I mean, this part. This part is actually equivalent to this, okay? Are you guys following this? And maybe if your application is changed to have different number of classes, or if you want to change the number of bounding box estimated from the each grid, then this dimension, the 30, might be changed. You can manipulate that. And also even you can, if you want to change the grid size to maybe 10 by 10, then that dimension also be changed like this, okay? So anyways, this dimension that could be manipulated by yours, right? So this is the YOLO, the first part of the YOLO, this part, okay? And I will explain why that bounding box information is composed of 5-dimensional vector here. So when defining one bounding box, you may have to specify its center point, center's XY coordinate. Okay. So for that, we reserve 2 dimensions. And for remaining 2, we have to contain the width and height of the bounding box. Okay. So this is kind of intuitive, right? For specifying some bounding box with arbitrary size, you have to specify their center XY coordinate and their width and height to properly describe the bounding box, okay? And the fifth information is their confidence value. So confidence value, it is actually meaning this. So, I mean, if this value is having the value from 0 to 1, okay, we will first make the ground truth and then train this fifth dimension as well. But how to make that ground truth is denoted here. So, I mean, if we estimate, so the first part is that bounding box, we have to specify for this grid, for this specific grid, we have to decide this grid is having object or having only the background images. Okay, so maybe you already seen that here, for example, in this image, the ground truth bounding boxes are limited. There is only three ground truth object bounding boxes in ground truth, right? But we will estimate this number of bounding boxes, okay? And maybe for these regions, not this region, maybe this region, if we estimate two bounding boxes from this region, that bounding box might have the background object. They don't have any foreground object, such as car, bicycle, or dog, right? Are you guys agree with this? Okay. So, I mean, these P are the probability for class. This means maybe for this grid, it would be 1. And for this grid, this value would be 0. Okay. So somehow when training the network, we know that grid is having the object inside or not. Okay. And we can, we can decide this value either to 0 or 1. Okay. And also we have to also reflect the IOU things. Okay. So this is meaning intersection over union. Okay, that is the IOU. So when doing the object detection, you will frequently see this intersection over union. But this is not that difficult concept. So when given two bounding boxes, this IOU is measuring their equivalence. Okay? So we are frequently use L2 laws, which is the mean square error laws or the Euclidean laws, to measure the accuracy of the prediction and ground truth. L2 is the measure for calculating the distance between prediction and ground truth, right? IOU is also the measure for calculating the distances between these two bounding boxes. Okay? And how they calculate is we can get both intersected region. This is the intersection and this is the union. Intersection means how much two bounding boxes are intersected. We calculate those regions which is intersected by two bounding boxes. And union means they're, merged. This is the merged new some polynomial, right? And their region, that is union, okay? And intersection over union means we will calculate the intersected region and divide it by the union. This is the intersection over union measured. If you calculate this, this will have the maximum value 1, which is 1, when intersected value is same as the union. Okay, so if IOU is 1, two bounding boxes are maybe becoming identical. Okay. I agree with that. because their union is same as intersection. Their intersected region is same as the union region. If these two are same, then those two bounding boxes have to be same. Okay. And if this goes to zero, I mean, if this value is 1, then it means those two bounding boxes are actually same. And if IOU is becoming 0, it means there is no intersected region. Okay, so the two bounding boxes are totally different. Okay, so anyways, totally different. Okay, so IOU is the measure for calculating the distance between two bounding boxes. Okay, are you guys understanding this? Okay, and what I mean denoted here, the IOU, the predict and ground truth. This means we during the training we have to calculate two bounding boxes. Maybe for this region, we may estimate two bounding boxes, right? And we have to measure the IOU between these bounding box and some of the ground truth bounding box, right? And then use this value as the ground truth for training the fifth value of that prediction. Okay. But the thing is, you may already understand that this becomes the probability for object needs that would become 0 if there's no object inside this grid. Okay, so for example, this may have 0, 0, 0, 0. This PR class might have 0, almost 0 for these regions, and only have 1 when that grid have the here there's bicycle object and this is car object, right? Here that would be 0 and this part it would have 1, right? And for this grid, it may have the ground truth bounding box. And if we here, if this region predict two bounding box, then those two bounding boxes are used to calculate this IOU. And actually, when estimating this, four values, it also estimates that those two bounding boxes confidence value. Okay, and this confidence value becomes completely 1 when there is an object in the grid, and at the same time, their IOU is same as the ground truth bounding box. Unless if the bounding box is different from the ground truth, it may have some values from 0 to maybe 0.5 or something. Okay. Anyways, this fifth value is actually estimating the confidence or some accuracy of the bounding box. Okay. Anyways, it estimated during the inference time. Okay. So this fifth is bit not intuitive, but I hope you can understand this as well. Okay, so that is YOLO. So because of that, the one bounding box have 5-dimensional information, okay, for YOLO prediction. So, I mean, for each bounding box, we estimate 5-dimensional vector, and also we classify each grid using the number of class, okay? And then we may estimate for each grid, we will estimate this number of this dimensional class probability vector, and there will be 98 bounding boxes estimated, okay? And this is actually the loss function of the YOLO, okay? And you can see this can see this part is, closing the estimated XY position of the bounding box, the center position of the bounding box to its ground truth. Okay, so that's happening here. And this part also closing the width and height of the bounding box to their ground truth. Okay, so this is actually training the bounding box part. Okay, and also you can see this kind of notation. So this B is 2 because you will estimate 2 bounding boxes for each grid. Okay, and also this S is meaning 7 because you have to calculate this loss for all the grid. Okay, so we will have totally 98 bounding boxes. So S squared, that would be 49, okay? And we will estimate 2 bounding boxes. So we have to apply this loss for all the bounding boxes estimated from each grid. Okay. And also this is denoting that this one notation, this is denoting that there is object in that grid. Okay, so that have the ij index, right? I is for grid index. This is for grid index, and J is for bounding box index. And I mean, this one will be made either this would be have only a value either 0 or 1, depending on the fact that that grid is having object inside or not. Okay, if that grid have the object, then this value becomes 1, and we apply the bounding box rules for that grid. But if that grid is not having object ground truth, then this value becomes 0, and we will not apply this rules, which is the bounding box rules for that grid. Okay. So this is same for this part. So these two are the bounding box rules. Okay. And another thing is this is more easier, so I will explain this first. So this part we have to loop through all the grid. So this is looping for all the grid, and this would be 1 if the grid has the object inside, and this would be 0 if there is no object inside that grid. And we apply this only when that grid has the foreground object. Okay, if that grid have the foreground object, we estimate their class probability. Okay, so instead of using the cross entropy laws, they use the L2 laws to close this vector to one hot encoded ground truth. So maybe this vector will be like this, having the 20 dimension, but having just 1 for ground truth class. Okay, so for the probability prediction, we are closing that to one hot encoded ground truth. Okay, so this is the class probability loss. Okay, and here is the confidence value we have to also train, right? Okay, and as I told you, this value is actually having this value. Okay, this is the confidence value, which is used as the ground truth. So if it is non-object grid, which may not have the object inside, then this value becomes 0. Okay, and if this is the grid which have the object inside, then this value would become 1 multiplied by their IOU. Okay. So actually we are estimating the bounding boxes accuracy as well when estimating the confidence value. Okay. So this is the loss function that can train this network. Okay. So using this, given one image, you will estimate this dimensional array. You can, of course, change the dimension by manipulating the hyperparameter. But for this setting, this dimensional array is estimated from the image. And then you can get this amount of bounding box and the probability for each region. Okay. And you can also feel that these two information is estimate simultaneously. Okay. Getting this array that happens simultaneously, right? Are you guys agree with that? Okay. This is the class probability, and this is the bounding box information, and they are collected jointly at the same time. Okay. 이해되고 있나요? 다들 졸린 것 같은데. I think most of are sleepy, maybe. Are you guys really following this? Okay. Please raise your hand if you are not following. Maybe nobody will raise your hand. But then, is there anybody who fully understands this? Please raise your hand. Nobody? Then most are in the middle. I mean, is this difficult or not? Easy? Medium? Okay. Difficult? Maybe not. Okay. YOLO is actually easy. I mean, compared to the fastest, not fastest, compared to the RCNN, fast RCNN and fast RCNN, this YOLO is more easy. They involve just one architecture to train estimate all the information, the probability for the grid, and also the bounding box. Okay. And after estimating this array from the image, then if you visualize that, that looks like this. Okay. For the foreground, for the background grid, there would be no bounding box appeared. But for the foreground grid, there will be very many bounding boxes appeared. Okay. And somehow you have to apply some post-processing algorithm whose name is non-maximal suppression. We frequently call it as NMS to make the result like this. So which kind of algorithm may require here? If you think about that, then very simple algorithm is required actually. Among these regions, I mean, here there are many bounding boxes, but they are have many intersections each other. Okay, so we will that non-maximal suppression is doing picking just one bounding box, which may have the highest confidence value. Okay, I mean, we normally if two bounding boxes are having the high IOU, I mean, anyways, we may have the threshold value, which is decided in the heuristic manner, but the confidence value is from 0 to 1. So normally the threshold might be around 0.7 or something. Okay, so if two bounding boxes, their IOU are over this threshold, then it means two bounding boxes are close each other. And among these two bounding boxes, we pick one bounding box which have the higher confidence value. Okay, then the box which have the highest confidence value will only remain like this. Okay, are you guys following this? Okay. So that's actually happening here. And this is the code for NMS, actually. So basically what they does here is they also calculate the IOU value here. So intersection will be, these oversected regions width and height, we will multiply them. And this is the union regions, their region anyways. So we somehow first sort this order, which contains the confidence value for all bounding boxes, which is estimated from the network. We first sort that by the confidence value and somehow remove whose IOUs are remove the boxes which have lower scores. So that is actually happening in this code. Okay, so this is actually very short. It loop until just one will be remained, and it removes the bounding box which have the higher IOUs and lower confidence value. Okay. It loops through until the one bounding box will be returned. Okay. So that's the non-maximal suppression algorithm, which is the post-processing. But I mean, that NMS is not differentiable, right? Okay, this NMS is reasonable, but this is not differentiable, and this may cause some suboptimality. So later in object detection pipeline, we will actually try to remove this NMS part as well. Okay. And this is some of the comparison for YOLO to previous algorithms. So we already learned about RCNN, fast RCNN, and also the faster RCNN algorithms. And the x-axis, they are denoting frame per second, which is the speed. So how many frames they process per each second. So if this value is high, then it means that algorithm is having the high speed. Okay. So how many process you can do per second. Okay. If you do many process, then this value will have the high value, right? So higher speed, if the algorithm have, then it goes right. Okay. And this is the accuracy value, precision value. So higher is better. So RCNN, the original RCNN is slow compared to the fast RCNN. Okay, so it is in the left part of the fast RCNN, and their accuracy is also limited. But fast RCNN, they are slightly right side of the RCNN, and also their accuracy is also greatly improved compared to the RCNN. And also the fast RCNN actually there are some trade-off if they use big backbone or small backbone. Their algorithm have trade-off between speed and accuracy, but if they use ResNet backbone, the speed and accuracy would be like this. If they have different backbone, their speed and accuracy would be here. But anyways, they are faster than fast RCNN, and their accuracy is far better than the fast RCNN and the RCNN algorithm. Okay, so this is the RCNN algorithms. And YOLO was here. Okay? YOLO that we just learned is here. So it's very fast because it is one-stage algorithm. But the thing is, its performance is less than that of the RCNN. Okay, but YOLO is continually improved. Okay? There are version of for this YOLO, and now we have YOLO version 11. Okay, actually. So this algorithm is first appeared in 2016, but there was a gradual improvement, and now we have YOLO version 11, and it has both good accuracy and speed. YOLO version 2, it already have the very good speed, and also you can see their accuracy is better than the faster RCNN algorithm. Okay, so many industrial environment, the YOLO works very well actually, and also at the same time they are providing the real-time speed. So many people are getting aware of this algorithm and try to use this in the practical and real-world situation, and it works very well actually. Okay, so and also, but maybe we will cover YOLO version 2 and version 3 in the remaining classes. We will see what components have been changed from the YOLO, original YOLO, and how they improve the performance. Okay, but the most dramatic part, which is improved for YOLO version 2 and 3, was their recall. So I didn't tell about the recall. There are actually two measures for measuring the accuracy. So precision and recall. I will explain it in this slide. Okay, but precision, the YOLO is already not bad. But the important problem in YOLO algorithm is their recall is very limited. Okay. So in YOLO version 2 and 3, they are focusing on improving the recall of the YOLO. Okay. And to say this more properly, I have to explain these two concepts, recall and precision. This is the two measurement for evaluating the performance of the system. So they're actually the accuracy. We normally measure the precision, but recall is also very important. And we can define recall and precision like this. Precision would be the ratio of total word you say, maybe the algorithm will output something, right? We will, we will say it as the word the people is outputting. Okay, we can say the precision might have this type of formula. Correct word. So we humans are saying something in our daily life, and we say correct word, and sometimes we say incorrect word, right? The ratio of correct word over the total word we say, that's kind of the precision, okay? So this is the good measure for measuring the accuracy of the system, okay? If people who lies a lot, we can evaluate that person as bad system, right? We will not trust him later, right? The machine learning algorithms are saying, if the machine learning algorithm say output, they output some wrong result, their ratio of wrong result are actually larger than the correct result, then we will not trust that system, right? So that's good measure of measuring the accuracy. But recall is also a very important aspect. So recall is defined like this. The truth and correct word. So it is defined as this. So our correct word are divided by the truth in the word. Are you guys understanding this? So, let's assume that some people have the high recall, but there could be a person that have the low recall, that have the low recall, but may have high precision. There could be a person like this, okay? I mean, if he speaks less, the truth in the world will not be fully covered by that person. Okay? He cannot tell all the truth in the world because he speaks less, right? But if he speaks, he always tell the correct word. In that case, that person have the high precision because he always tell the truth. But the truth in the world will not be properly covered by that person's word, right? In that case, that person is not also useful, right? In some sense, he's not also useful, but of course, this kind of system is also not useful. So if some person is covering the truth, let's say 90% of the truth is covered by some person's word, okay? But he speaks a lot more than the truth, okay? Let's say the number of truths, this is 100, let's assume like that. And she speaks 90 truths among 100 truths in the world, but she speaks, let's assume she speaks this amount of words every day, let's assume like that, then he only correct 90 among this amount of words she say every day. So her precision is very low, but because she speaks a lot, she has the high probability to tell the truth in the world. Okay, but this system is also not very desirable, right? Okay. So are you guys understanding the concept of recall and precision? Okay. We are have to have the system which have both high recall and high precision. Okay, so that's the concept of recall, and I will explain this part again. When analyzing the error of the YOLO, their characteristics is their bounding boxes themselves are also having error compared to the fast RCNN because they somehow simultaneously estimate the bounding box. So it is less accurate than the fast RCNN. And also, second important problem in the error statistics in YOLO is they have low recall. So they could have high precision, but their bounding boxes will not cover all the objects in the images. So let's say in the image, there are many objects, foreground objects, humans and dogs, and some car, right? We have to train the object detector to capture all person and object inside. But YOLO tend to miss some of the other objects. But if we predict something, their precision is not bad, okay? But if frequently miss some object in the images. This is the problem of YOLO, and this happens because they only estimate this number of bounding boxes. So 98, this could be large in number if there are only a few objects, like 5 objects, then this amount of bounding box might be enough. But if there are objects even more than 100, then this bounding box is already insufficient. Okay, are you guys agree with this? So in later versions of the YOLO, they try to increase the number of bounding boxes, and also they have some more, techniques to improve, anyways, the accuracy of the YOLO. Okay. So actually, this is the end of today's lecture. And maybe also next class, we will also learn about the more recent object detection pipeline based on the transformer architecture. And after this, we will also learn about the real-time object detection algorithm, which is also the YOLO. And also, we can also transform the transformer architecture to have the real-time speed. So we will learn about such techniques. Okay. Okay. Thank you, and see you next Monday. 잠시만요.